At 12,000 feet over the English Channel on July 19, 1940, Flight Lieutenant James Lethart watched the Messerschmitt Bf 109 drop away from him in a steep dive. He had achieved the perfect firing position, the German pilot banking right. Lethart positioned above and behind, with clear sight lines and closing range. In perhaps 3 seconds, he would have a gun solution that no competent pilot could miss. Then the German simply pushed his stick forward and dove. Lethart followed, rolling his Spitfire inverted to bring the nose down sharply, maintaining visual contact with his target. The maneuver was textbook pursuit geometry. What happened next was not in any training manual. His Merlin engine coughed once, sputtered, and died completely. At 10,000 feet, with a German fighter escaping below him and the Channel waiting beneath, Lethart found himself flying a powerless glider. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Rolls-Royce Merlin engine, source of the Spitfire's legendary performance, had betrayed him at the worst possible moment. The phenomenon would be reported dozens of times in the coming weeks. British pilots achieving advantageous positions, German pilots executing negative G maneuvers, diving away inverted, or pushing into steep descents, and the Spitfire's engine cutting out precisely when power mattered most. By August 1940, this wasn't a mysterious mechanical failure. It was a tactical crisis threatening Britain's ability to defend its own airspace. The problem wasn't poor engineering or inadequate design. The Merlin was among the finest piston engines ever developed, capable of producing over 1,000 horsepower and powering aircraft to speeds exceeding 350 miles per hour. The issue was physics, specifically the behavior of fuel under negative gravitational force. The Merlin used an SU float-type carburetor, a proven system for mixing fuel and air in the correct proportions. Under normal flight conditions, positive G loading, where acceleration pushed pilots into their seats, the float valve mechanism worked flawlessly. Fuel flowed from the tank through the carburetor's float chamber, maintained at the correct level by a brass float that opened and closed the fuel inlet valve. But when a pilot pushed the stick forward sharply, executing what aviators called negative G flight, everything inverted. The fuel in the float chamber surged upward, away from the jets that fed the engine. The float, designed to regulate fuel level under positive G conditions, now floated uselessly at the top of the chamber. The engine, starved of fuel despite full tanks just feet away, quit within seconds. German pilots flying Messerschmitt Bf 109s and Focke-Wulf 190s faced no such limitation. Their Daimler-Benz 601 and BMW 801 engines used direct fuel injection systems. Fuel was pumped under pressure directly into the cylinders, independent of gravity. A German pilot could push negative G, roll inverted, dive at any angle, and his engine would continue producing full power throughout the maneuver. This asymmetry created a profound tactical advantage. When a British pilot achieved a firing position, the German pilot's escape option was simple and effective. Push into negative G flight, either by rolling inverted and pulling, or by simply pushing the stick forward into a bunt. The pursuing Spitfire or Hurricane pilot faced an impossible choice: follow the maneuver and lose engine power, becoming vulnerable and potentially fatal, or break off pursuit and watch the enemy escape. The mathematics of aerial combat are unforgiving. An engagement typically lasted between 20 and 40 seconds from initial contact to either victory, escape, or death. Within that window, achieving and maintaining a firing position required continuous power. Any interruption, even 2 or 3 seconds without thrust, meant loss of airspeed, loss of position, and transformation from hunter to hunted. Britain entered the summer of 1940, facing an existential threat that had nothing to do with carburetor design. The fall of France in June left the British Isles isolated, with the Wehrmacht controlling the European coastline from Norway to the Spanish border. The Royal Air Force represented the primary barrier between German invasion plans and British soil. Fighter commands approximately 600 operational Spitfires and Hurricanes were tasked with defending British airspace against the Luftwaffe's 2,000 aircraft concentrated in occupied France and the Low Countries. The strategic situation demanded that British fighters achieve maximum effectiveness from each combat sortie. Luftwaffe formations crossed the Channel daily, targeting RAF airfields, radar stations, and aircraft production facilities. Fighter Command could not afford to let German aircraft escape once engaged. Every Dornier bomber that reached its target inflicted damage on Britain's ability to continue fighting. Every Bf 109 that escaped an engagement remained available to escort future raids. The carburetor problem undermined this strategic imperative. German pilots learned quickly that British fighters couldn't follow negative G maneuvers without engine failure. Luftwaffe tactical doctrine incorporated this knowledge. When bounced by Spitfires or Hurricanes, German pilots would execute bunts or split-S maneuvers, using negative G flight to disengage before British fighters could achieve firing solutions. Fighter Command's tactical doctrine emphasized energy management and position advantage. Pilots were trained to attack from altitude, using gravity and engine power to achieve superior speed. They learned deflection shooting, formation discipline, and how to exploit the Spitfire's excellent turning performance against the Bf 109's wider turning radius. None of this training addressed what to do when the engine quit during the most critical phase of combat. Squadron commanders began receiving reports in late July 1940, pilot officer accounts describing clean shots that dissolved when engines failed. Flight logs noting multiple instances per sortie. Engineering officers examined aircraft that showed no mechanical defects, yet pilots insisted the engines had been cut out during combat. The problem's scope became undeniable during the intensive fighting of August 1940. On the 12th, Luftwaffe formations attacked RAF airfields across southern England in waves. Spitfire and Hurricane squadrons scrambled repeatedly, engaging German fighters at altitudes between 10,000 and 20,000 feet. After-action reports from multiple squadrons mentioned the same phenomenon, engines cutting out when pursuing diving German aircraft. Flight Lieutenant Bob Stanford Tuck of 92 Squadron filed a particularly detailed account. He had engaged 3 Bf 109s north of Manston, achieving firing position on the rearmost aircraft. The German pilot rolled inverted and pulled through into a vertical dive. Tuck followed, rolling his Spitfire to track the target. His engine stopped immediately. He managed to restart it after falling through 2,000 feet, but the German fighters had escaped and Tuck found himself alone, low on fuel, with uncertain engine reliability. These weren't isolated incidents involving inexperienced pilots. Veterans with hundreds of flight hours reported identical experiences. The pattern was consistent. Negative G maneuver, immediate engine failure, restart possible after rolling back to positive G flight. The duration of the power loss varied from 2 seconds to 15 seconds, depending on how quickly the pilot could restore positive G conditions and how much fuel had surged away from the carburetor. Jets. Squadron leader Douglas Bader of 242 Squadron, who flew with artificial legs after losing both limbs in a pre-war flying accident, documented the problem in his combat reports. On August 30th, 1940, Bader engaged a formation of Bf 109s south of London. He achieved firing position on one German fighter, only to have his engine quit when the enemy pilot bunted into a dive. Bader noted in his report that the German pilot appeared to execute the maneuver deliberately, as if he knew British fighters couldn't follow without engine failure. The Royal Air Force faced a dilemma that couldn't be solved through pilot skill or tactical innovation. British fighters had excellent performance characteristics, better turning radius than the Bf 109 at most speeds, superior low-altitude acceleration, robust construction that could absorb battle damage. But these advantages meant nothing if German pilots could escape at will by exploiting a fundamental engineering limitation. The implications extended beyond individual combat encounters. RAF Fighter Command operated on a defensive footing throughout the Battle of Britain. British fighters scrambled in response to radar detection of incoming German formations. They climbed to intercept altitude, engaged the enemy, and either destroyed German aircraft or forced them to abort their missions. The system worked only if British fighters could convert tactical advantages into confirmed kills. If German fighters could routinely escape once engaged, the entire defensive strategy became questionable. Luftwaffe bomber formations would reach their targets more frequently. Fighter command's loss rate would increase as British pilots found themselves unable to press attacks home. The arithmetic of attrition would shift in Germany's favour. Technical officers at the Royal Aircraft Establishment at Farnborough understood the carburettor problem. Solving it, however, required either completely redesigning the fuel system impossible during wartime production or finding a way to prevent fuel starvation during negative G flight while maintaining the carburetor's normal operation under all other conditions. The Merlin's SU carburetor was a sophisticated piece of engineering. Designed in the mid-1930s, it represented the standard British approach to fuel delivery for high-performance piston engines. The float chamber maintained fuel at a constant level through a brass float that opened and closed the inlet valve. Fuel flowed from the float chamber through precisely calibrated jets into the carburetor throat, where it mixed with incoming air. The mixture then entered the engine cylinders for combustion. Under positive G conditions, this system worked flawlessly. The float settled at the bottom of the chamber, maintaining proper fuel level. Jets delivered fuel at the rate the engine required. Throttle response was instantaneous. The carburetor could handle everything from idle power to maximum combat output without hesitation. The design assumed aircraft would spend the vast majority of flight time under positive or neutral G loading. Fighters maneuvered aggressively, certainly, but most maneuvers involved positive G turning, climbing, pulling out of dives. Negative G flight was considered rare and brief. The carburetor wasn't designed to handle sustained negative G operation because such conditions weren't expected to occur frequently in combat. This assumption proved catastrophically wrong once the Battle of Britain began. German pilots discovered they could exploit negative G flight to escape British fighters. What should have been a minor design limitation became a decisive tactical advantage. Rolls-Royce engineers examined several potential solutions in August 1940. One approach involved adding a small auxiliary fuel pump to maintain pressure during negative G flight. The pump would activate when the aircraft's attitude indicated negative G, forcing fuel to the carburetor jets even when the float mechanism failed. This solution had merit but required complex mechanical components, electrical systems to detect negative G conditions, and extensive testing to ensure reliability. Another proposal suggested redesigning the float chamber with internal baffles. The baffles would prevent fuel from surging away from the jets during negative G, maintaining enough fuel near the outlet to keep the engine running. This approach required manufacturing new carburetors, a process that would take months and interrupt Merlin production at a time when Fighter Command desperately needed every available engine. A third option involved switching to a pressure carburetor system similar to those used in some American aircraft. Pressure carburetors delivered fuel under positive pressure rather than relying on float-controlled gravity feed. They handled negative G flight without problems, but pressure carburetors were heavier, more complex, and would require complete redesign of the Merlin's fuel system. Implementation would take a year or more. Each approach had the same fundamental problem: complexity, production delays, and uncertain effectiveness under actual combat conditions. Britain needed a solution that could be implemented immediately, didn't require manufacturing new components, and would work reliably in the hands of combat pilots who had no time for temperamental equipment. The solution would not come from senior aeronautical engineers at established research facilities. It would come from a 33-year-old woman working at the Royal Aircraft Establishment, someone who had never designed aircraft engines but understood fluid dynamics and mechanical systems with exceptional clarity. Beatrice Schilling was not supposed to be designing anything that affected combat operations. Her official title was Scientific Officer in the Department of Engine Research and Development. In 1940, women in technical positions at government research establishments typically handled documentation, performed calculations that male engineers specified, or managed administrative tasks that freed men for more important work. Schilling had different ideas about her role. Born in March 1909 in Hampshire, she demonstrated early aptitude for mathematics and mechanical systems. Her parents, working class but supportive, encouraged her education despite prevailing assumptions about appropriate careers for women. She attended the University of Manchester, earning a degree in electrical engineering in 1932 when fewer than 2% of engineering graduates were women. The path to that degree had not been straightforward. British universities in the 1920s and early 30s admitted women to engineering programs reluctantly. Some professors refused to allow women in their laboratories. Industrial firms that might employ graduate engineers made clear they had no interest in hiring women for technical positions. Schilling completed her degree knowing she faced systematic barriers that male graduates never encountered. After graduation, she pursued postgraduate research in engineering while simultaneously developing a passion for motorcycle racing. She competed in speed trials at Brooklands, the famous motor racing circuit in Surrey, riding supercharged motorcycles that she had modified herself. In 1934, she achieved speeds exceeding 106 miles per hour on a Norton motorcycle she had personally tuned and optimized. This combination advanced technical education and hands-on mechanical experience was unusual for anyone in 1930s Britain. For a woman, it was nearly unprecedented. Schilling understood engines not just as theoretical systems, but as physical machines that could be modified, tuned, and improved through direct experimentation. The Royal Aircraft Establishment hired her in 1936, initially for general research work. Her supervisors quickly recognized her capability with complex mechanical systems. By 1938, she was working directly on engine development problems, analyzing carburetor performance and fuel flow characteristics. She brought to this work a perspective that differed from her male colleagues. Most aeronautical engineers approached problems through established methodologies, consulting reference texts, applying known design principles, developing solutions that adhered to conventional engineering practice. Schilling's motorcycle racing experience had taught her a different approach. Identify the specific problem, understand the physical constraints, and find the simplest solution that actually works. When the Merlin's -G problem became critical in August 1940, Schilling was among the engineers examining possible solutions. The challenge was precise: prevent fuel starvation during -G flight without degrading engine performance under normal conditions. The carburetor needed to function properly during +G maneuvers, level flight, and -G situations. Any solution that fixed one problem while creating others was unacceptable. She attended meetings where senior engineers discussed auxiliary pumps, baffled float chambers, and pressure carburetor conversions. The proposed solutions were technically sound but impractical. They required months of development time, complex manufacturing processes, and extensive flight testing. Britain didn't have months. RAF Fighter Command was losing aircraft daily. Every week without a solution meant more German fighters escaping, more British pilots killed, more damage to Britain's ability to continue fighting. Schilling's solution emerged from a different way of thinking about the problem. Instead of asking how to maintain normal carburetor operation during -G, she asked a simpler question. How do we keep enough fuel near the jets to prevent complete engine failure? The answer was a flow restrictor. She proposed installing a small brass disc in the fuel line between the float chamber and the carburetor jets. The disc would have a precisely calibrated hole through its center. Under normal +G conditions, fuel would flow through the restrictor hole at the rate the engine required. The float chamber would maintain its designed fuel level, and engine performance would be unchanged. During -G flight, when fuel surged away from the jets, the restrictor would limit how much fuel could escape the lower part of the float chamber. The restricted hole was too small to allow rapid drainage. Enough fuel would remain near the jets to keep the engine running, even when the float mechanism failed to maintain proper level. The engineering elegance was in the calibration. Too large a restrictor hole, and fuel would still surge away during -G flight, leaving the engine starved. Too small a restrictor hole, and the engine wouldn't receive enough fuel during high-power operations like takeoff or combat climbs. The hole diameter had to be precise, large enough for full power operation under +G, small enough to prevent complete fuel drainage under -G. Schilling calculated the optimal diameter at 0.06 inches, a brass disc with a hole barely wider than the thickness of a penny. The proposal met skepticism. Several senior engineers argued that restricting fuel flow was fundamentally wrong. The solution to fuel starvation couldn't be making it harder for fuel to reach the engine. Others worried about high-altitude performance, where the carburetor already operated near the limits of fuel delivery capability. Adding any restriction might cause power loss at 20,000 feet or higher. The theoretical objections had merit. Conventional engineering practice suggested that any restriction in fuel flow would degrade performance. The carburetor was designed to deliver fuel at specific rates under various conditions. Deliberately impeding that flow seemed counterproductive. Schilling's response was to build a prototype and test it. Engineering theory mattered less than measurable results. If the restrictor worked under actual operating conditions, theoretical objections were irrelevant. If it failed, the testing would reveal exactly how and why, providing data for refining the design. She fabricated the restrictors herself, machining brass discs and drilling the .06-inch holes with precision equipment. The manufacturing process was straightforward. Each disc measured approximately 1 inch in diameter and 1/8 inch thick. The hole was drilled dead center and chamfered slightly on both sides to prevent rough edges from disrupting fuel flow. Total manufacturing time per restrictor, approximately 15 minutes. In late August 1940, she installed a restrictor in a Merlin engine mounted on a test stand at Farnborough. The initial tests measured performance under simulated flight conditions. The engine ran at various power settings while the test stand tilted to simulate different aircraft attitudes. Under positive G conditions, the stand tilted to push fuel toward the carburetor. The engine performed identically to an unmodified Merlin. Maximum power output was unchanged. Fuel consumption matched specifications. Throttle response was normal. Then the test stand tilted nose down, simulating negative G flight. The unmodified Merlin would have quit within seconds. The modified engine continued running. Power output dropped slightly, perhaps 5 to 10%, but the engine kept producing thrust. When the stand returned to positive G attitude, full power resumed immediately. The test results were promising but not conclusive. A test stand couldn't replicate actual combat conditions. Real validation required flight testing with a pilot executing combat maneuvers, particularly the aggressive negative G situations that caused engine failure during pursuit of diving German fighters. Schilling convinced her supervisors to authorize flight tests in early September 1940. A Spitfire was modified with the restrictor installed, and an experienced test pilot was briefed on the evaluation protocol. The pilot would perform a series of maneuvers designed to cause engine failure in an unmodified aircraft, sharp pushes into negative G flight, inverted flight with forward stick pressure, rapid transitions from positive to negative G loading. The test pilot took off from Farnborough on September 4, 1940, and climbed to 15,000 feet. The first test maneuver was a simple bunt, pushing the stick forward sharply to create negative G. In an unmodified Spitfire, this would cut the engine immediately. The modified aircraft's engine coughed slightly, lost perhaps 10% power for 1 second, then continued running normally. Subsequent tests grew more aggressive. The pilot rolled inverted and pulled hard, creating sustained negative G conditions while in a diving turn. The engine ran throughout the maneuver. He executed a split S rolling inverted and pulling through into a dive while advancing the throttle to maximum power. The engine maintained thrust. Finally, he simulated pursuit of a diving target, rolling inverted to follow a steep descent while maintaining visual contact with an imaginary enemy below. The Merlin kept running. The flight test report documented 18 separate negative G maneuvers. In every case, the engine continued operating. Power output decreased during sustained negative G, typically by 5 to 15%, but never failed completely. When the aircraft returned to positive G flight, full power resumed within 1 second. The restrictor worked exactly as Schilling had calculated. On September 6, 1940, the Royal Aircraft Establishment issued a technical note recommending immediate installation of the restrictor in all operational Spitfires and Hurricanes. The note specified the exact dimensions of the restrictor disc, installation procedures, and expected performance characteristics. Manufacturing was authorized to begin immediately. The device acquired an unofficial name among RAF personnel, Miss Schilling's Orifice. The name was partly respectful acknowledgement of Schilling's engineering achievement, partly the kind of irreverent humor that military personnel apply to any technical device, and partly a reflection of the casual misogyny that pervaded engineering and military environments in 1940. The term orifice, anatomically suggestive, reduced a significant technical accomplishment to a crude joke. Schilling apparently found the nickname amusing rather than offensive. She understood that widespread adoption mattered more than respectful terminology. If crude humor helped mechanics remember to install the restrictors properly, that served the larger purpose of keeping pilots alive. Production began immediately at multiple manufacturing sites across Britain. The restrictors were simple enough that any machine shop with basic capabilities could produce them. Brass stock was readily available. The drilling and chamfering required precision but not exotic equipment or specialized expertise. Within a week, thousands of restrictors were being distributed to RAF maintenance units. Installation was equally straightforward. Mechanics removed the carburetor, disconnected the fuel line between the float chamber and the jets, inserted the restrictor disc, and reconnected the line. The entire process took less than 30 minutes per aircraft. No special tools were required. No complex calibration was necessary. The restrictor was installed, the aircraft was tested on the ground, and it was returned to operational status. By mid-September 1940, RAF maintenance crews were installing restrictors in operational aircraft across Fighter Command. Priority went to frontline, squadrons actively engaged in the Battle of Britain. Spitfire and Hurricane units based at airfields in southern England received the modifications first. The installation proceeded squadron by squadron, aircraft by aircraft, as maintenance schedules allowed. Pilots noticed the change immediately during their first combat sorties with modified aircraft. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Flight Lieutenant Eric Mars of 65 Squadron flew his first combat mission with a restrictor-equipped Spitfire on September 21, 1940. His squadron intercepted a formation of Bf-109s escorting Heinkel 111 bombers north of Canterbury. Mars achieved firing position on a Bf-109 at 14,000 feet. The German pilot bunted into a dive, the standard escape maneuver. Mars followed, rolling inverted to maintain visual contact. His engine didn't quit. He stayed on the German fighter through the dive, correcting his aim as the range closed. At 8,000 feet, he fired a 3-second burst from his 8.303 machine guns. The Bf-109's engine began trailing smoke. The German pilot bailed out at 5,000 feet. Mars climbed back to altitude, his engine running smoothly, and rejoined his squadron. The after-action report noted simply, "Engine performed satisfactorily during pursuit of enemy aircraft in -G dive." Similar reports began appearing from squadrons across Fighter Command. Pilots who had previously broken off pursuit when German fighters bunted now followed through the maneuvers. German escape tactics that had been effective in July and August became substantially less reliable in September and October. The tactical implications were immediate and measurable. RAF loss rates decreased as British pilots could press attacks home without fearing engine failure. German loss rates increased as their primary defensive maneuver became less effective. The asymmetry that had favoured the Luftwaffe throughout the summer disappeared. Luftwaffe intelligence officers noted the change. Combat reports from German pilots mentioned British fighters following through -G manoeuvres that previously would have caused pursuit to break off. Analysis of British aircraft wreckage revealed the installation of small brass discs in fuel lines. The Germans understood what had happened. A simple mechanical fix had eliminated their tactical advantage. The Battle of Britain's outcome wasn't determined by Miss Schilling's restriction alone. Fighter Command's tactical doctrine, radar-directed interception, pilot training, and aircraft production all contributed to Britain's survival. But the restrictor solved a specific, critical problem at a moment when solutions mattered desperately. It kept engines running during the exact maneuvers where they had previously failed. It allowed British pilots to exploit the Spitfire's performance advantages without crippling limitations. The device remained in use throughout the war, installed in thousands of Merlin-powered aircraft, even after Rolls-Royce developed more sophisticated solutions, pressure carburetors, improved float mechanisms. Many aircraft retained the original restrictors. They worked, they were reliable, and replacement wasn't necessary unless the carburetor required complete overhaul. Beatrice Shilling continued working at the Royal Aircraft Establishment throughout the war and well into the 1960s. She conducted research on engine performance, supersonic aerodynamics, and aircraft systems. She received the Order of the British Empire in 1948 for her contributions to aircraft engineering during the war. Her motorcycle racing continued into the 1950s, competing in trials and reliability runs. The irony was not lost on those who knew her story. British engineering establishments employed thousands of men with advanced degrees, extensive research experience, and official authority to develop solutions for critical problems. The solution to one of Fighter Command's most pressing tactical limitations came from a woman whose official role was supposed to be subordinate and supportive. She identified the problem correctly, not how to maintain normal carburetor operation during abnormal flight conditions, but how to prevent complete fuel starvation during brief negative G episodes. She designed the simplest possible solution, a brass disc with a small hole. She tested it systematically and proved it worked. The entire development process, from concept to operational deployment, took less than 3 weeks. The engineering achievement wasn't just the restrictor itself, it was recognizing that complex problems sometimes have simple solutions if you ask the right question. Auxiliary pumps, baffled chambers, and pressure carburetors would all have worked, eventually, after months of development. The restrictor worked immediately because it didn't try to redesign the carburetor, it just prevented the specific failure mode that caused problems during combat. Flight Lieutenant James Leithart, who had lost his engine while pursuing a Bf 109 in July 1940, flew throughout the remainder of the Battle of Britain and survived the war. His aircraft received Miss Shilling's restrictor in mid-September. He recorded 5 confirmed victories in October 1940, several involving pursuit of German fighters through negative G dives. His logbook for October 14, 1940, includes a notation: "Engine performed perfectly during vertical pursuit. The device works as advertised." The device he referred to was a brass disc, 1 inch in diameter, 1/8 inch thick, with a hole 0.06 inches across. It weighed less than 1 ounce. It cost approximately 2 shillings to manufacture. It required no maintenance, no calibration, no special handling. It was installed in fuel lines across Fighter Command, and it kept engines running when they needed to run. The story of Miss Shilling's orifice represents something beyond standard wartime innovation narratives. It wasn't about massive industrial production, advanced technology, or revolutionary engineering. It was about correctly understanding a problem and implementing the simplest effective solution without regard for conventional approaches or institutional hierarchies. In summer 1940, Britain faced an enemy with superior tactical options due to a fundamental engineering difference. German fuel injection systems handled negative G flight perfectly, British carburetors didn't. The obvious solutions: redesign the carburetor, install complex auxiliary systems, switch to different technology would take months or years. The actual solution took 3 weeks and cost almost nothing. The German tactical advantage disappeared not because Britain developed better technology, but because someone understood that preventing total fuel starvation mattered more than maintaining perfect carburetor operation. 10% power loss during negative G was acceptable. Complete engine failure was not. The restrictor prevented failure at the cost of minor performance degradation. That trade-off proved decisive. German pilots continued using negative G escape maneuvers throughout the war. The tactics remained valid in other contexts, particularly against aircraft that lacked the restrictor modification. But against RAF fighters equipped with Miss Shilling's device, bunting into a dive no longer guaranteed escape. British pilots followed through the maneuvers, maintained firing positions, and achieved kills that would have been impossible 3 months earlier. The Battle of Britain's conventional narrative focuses on the RAF pilots who defended Britain against overwhelming odds. Their courage and skill were unquestionable, but courage and skill operated within constraints imposed by technology and engineering. When those constraints favoured the enemy, even the most skilled pilots faced impossible tactical situations. Miss Schilling's restriction didn't make British pilots more courageous or skillful. It removed a constraint that had prevented them from fully utilising their aircraft's capabilities. The Spitfire could always turn tighter than a Bf 109. It could always climb faster at lower altitudes. These advantages existed whether the engine ran during negative G flight or not. The restrictor simply ensured the engine kept running, allowing pilots to exploit advantages that had always been present. By November 1940, as the Battle of Britain transitioned into the night blitz, the negative G problem had essentially disappeared as a tactical concern. New Spitfires came equipped with restrictors during manufacturing. Existing aircraft had been retrofitted. Pilots flew with the confidence that their engines would function during any maneuver combat required. The Luftwaffe's daylight bombing campaign against Britain effectively ended in late October 1940. The reasons were multiple. Unsustainable aircraft losses, failure to destroy RAF fighter command, inability to achieve air superiority over southern England. Among those reasons, often overlooked, was the elimination of a tactical advantage German fighters had enjoyed throughout the summer. When German pilots could reliably escape British fighters by exploiting carburetor limitations, the loss exchange ratio favoured the Luftwaffe. British fighters shot down German bombers and fighters, certainly, but German fighters also shot down British aircraft or escaped when engaged. The arithmetic was survivable for Germany. When that escape option became unreliable in September and October, the arithmetic changed. British fighters could press attacks through the full engagement, maintaining firing positions during manoeuvres that previously would have forced them to break off. German loss rates increased. The campaign became unsustainable. Miss Schilling's orifice didn't win the Battle of Britain, but it removed an obstacle that had made winning substantially more difficult. It transformed a tactical liability into neutral capability. German and British fighters operated on equal terms regarding negative G performance. British pilots could then leverage their other advantages: superior turning performance at medium altitudes, robust aircraft construction, radar-directed interception, without artificial handicaps. The device remained classified throughout the war. Luftwaffe intelligence identified its existence and purpose, but British authorities never publicly discussed the restrictor or acknowledged the carburetor problem it solved. Official histories written after the war mentioned it briefly or not at all. Beatrice Schilling's name appeared in technical journals and engineering references, but not in popular accounts of the Battle of Britain. This silence reflected standard practice regarding technical solutions to combat problems. Acknowledging that British fighters had suffered from a significant design limitation might undermine public confidence in RAF capabilities. Explaining how a simple brass disc solved the problem might seem to diminish the complexity of wartime engineering. Crediting a woman for a critical innovation challenged prevailing narratives about who contributed to Britain's defence. The restrictor's very simplicity worked against its recognition. Complex solutions, radar, advanced aircraft designs, sophisticated tactics fit more easily into heroic narratives of technological achievement. A brass disc with a small hole seemed trivial by comparison, even though its operational impact was immediate and measurable. Beatrice Schilling understood this dynamic. She continued her engineering work without seeking recognition or challenging the institutional and hierarchies that marginalized her contributions. Her focus remained on solving problems rather than receiving credit for solutions. The restrictor worked. Pilots survived who might otherwise have died. That outcome mattered more than acknowledgement. She did, however, keep one of the original prototype restrictors as a personal memento, a brass disc, 1 inch in diameter, with a .06-inch hole drilled through its center. Simple, functional, effective, a physical reminder that engineering excellence sometimes manifests in the smallest, simplest solutions to complex problems. The story illustrates a broader truth about technological development during wartime. Conventional narratives emphasize revolutionary breakthroughs, radar, jet engines, nuclear weapons that represent fundamental advances in capability. These achievements matter, certainly, but wars are also won through countless small innovations that solve specific, immediate problems without fanfare or recognition. Miss Schilling's Orifice falls into this category. It didn't revolutionize aircraft design. It didn't represent a fundamental breakthrough in engineering knowledge. It solved one specific problem: fuel starvation during -G flight in Merlin engines with float-type carburetors. The solution was implemented quickly, worked reliably, and remained in use for years. This pattern repeated throughout the war across all combatant nations. Small modifications to equipment, minor adjustments to procedures, simple devices that addressed specific limitations. Individually, none changed the war's outcome. Collectively, they determined which side could effectively employ its technology and personnel under combat conditions. The German pilot who bunted away from James Leithart in July 1940 probably never learned that his escape maneuver stopped working reliably 3 months later. The tactical knowledge that -G flight would cause British engine failure remained valid in his mind. Perhaps he tried the same maneuver again in October or November and found a Spitfire still behind him, engine running, guns firing. Perhaps he never faced British fighters again. The historical record doesn't say. But across fighter command, pilots like Leithart flew with modified aircraft from September onward. They pursued German fighters through maneuvers that previously would have stranded them with dead engines. They achieved firing solutions and scored victories that engineering limitations had previously prevented. And they did this because someone understood that the problem wasn't carburetor design philosophy, but rather keeping enough fuel near the jets to prevent complete failure during brief -G episodes. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.